Greetings. I'm Goran Pavic from the National Institute of Science in Lyon, France. My presentation will be a sort of a follow-up of a talk on pipes presented in a COVID-free conditions at an earlier CAV meeting. While the earlier subject was rather broad, the current one will focus on some smart techniques aiming at in-situ pipe analysis. Pipes are everywhere, various sizes, various applications. We hate these, we enjoy these, we love these ones. Typical concerns in operation are seismic resistance, fatigue, corrosion, abrasion, fluid monitoring, etc. And the dynamical quantities which can help in monitoring the state of the pipes is pressure, vibration, strain, and stress. Safe operation of pipes is of major concern. Many techniques have been developed for the inspection and surveillance. These techniques are mostly of a local nature, looking at particular positions along the pipe, such as the position of a crack. On the other hand, modeling of dynamics of fluid-filled pipes has been in development since the end of the 19th century. So we have at this point the question, can we use a pipe model in combination with measurements to shift from a local to a global outlook? Here we recall some of the basic features of pipe dynamics. The distribution of pressure in the fluid and the motion of the wall can be quite complex. We can decompose these into waves. Three kinds of waves exist: the propagating ones and the idle ones, the latter being either evanescent or attenuating. Only the propagating waves carry energy. However, the evanescent or attenuating waves will, at a particular frequency called cut-on frequency, transform into a propagating wave. So the notion of propagating or idle depends on frequency. In the cross-section, each wave will exhibit a particular distribution of pressure and wall deformation. And these will be identified by two indices, a circumferential order n, which can be 0, 1, 2, etc., and radial order s, which is 1, 2, 3, and so on. We have here some examples of NS combinations which show the pressure distribution and the wall deformation of some of these waves. As I said previously, we need a model to carry out smart pipe analysis. A generic model of a pipe filled with a homogeneous fluid or gas can be constructed analytically. So the model depends on a number of input parameters, like the material constants of the wall, the constants of the fluid, and the diameter and thickness of the pipe. And of course, it assumes that the wall motion contains all three orthogonal components: axial, tangential, and radial. The nasty-looking governing equations produce equally nasty-looking solution, neither of which I intend to comment further. The solution is multivalued, with each term corresponding to one wave. The amplitudes of individual waves are unknown, as these depend on the boundary and excitation conditions, which vary from one case to another. On the contrary, the spatial distribution of interior dynamic pressure and wall displacements, which is supplied by the model, becomes perfectly known. It is just this relative distribution that we shall need in most of cases related to smart pipe analysis. Each wave is governed by three parameters: the circumferential order n, the radial order s, and the normalized frequency. The latter is Hertzian frequency f multiplied by three constants. And for a pipe of given material, the product of the diameter and the frequency is what matters more than the Hertzian frequency itself. For each wave, the model will provide axial and radial wave numbers, kx and kr, both function of omega, and fluid wall coupling factor, gamma, which is also a function of omega. The wave numbers are extremely useful, as these provide the spatial distribution of quantities we measure and analyze. The fluid wall coupling is also useful because we can infer what is taking place in the fluid by looking at the wall vibration. Here we have the laws which govern the pipe motion in three orthogonal directions: circumferential, axial, and radial. This is cosine in circumferential, exponential depending on the axial wave number kx, and in the radial direction it's Bessel functions depending on radial wave number kr. As the frequency increases, more and more idle waves, which we said are of no particular importance for us, because not carrying energy and being limited only to pipe extremities, turn into propagating waves. So at low frequencies, we shall have, therefore, only a few waves which can propagate. As a matter of fact, three types of coupled waves propagate at all frequencies: the pulsating one, the extensional one, and the flexural one. The pulsating wave is driven mostly by the fluid, while the other two mostly driven mechanically. We shall focus in this presentation at this pulsating wave, and we shall show how can we do some smart data processing in order to get useful information about the pipe. In particular, how to monitor state of fluid, how to monitor wall thickness, how to check sensor operation, and how to reconstruct hoop stresses in cases where this is of importance. Now, since the number of propagating waves increases with frequency, we can establish a frequency limit in terms of normalized frequency, where below this limit we shall have a simple behavior of the pipe, and above this limit the behavior will become more and more complicated. As a matter of fact, this limiting frequency is the cut-on frequency of the first higher order wave, which deforms in form of ovalization. However, the label low frequency may mislead. It concerns, as I said, normalized rather than Hertzian frequency. The low frequency limit may vary drastically depending on the diameter and thickness. This table shows the frequency limits for a number of pipe cases. If you look at the smallest pipe of 3/4 of an inch used in high pressure hydraulics, we see that the limit is 26 kilohertz. In other words, all the frequencies will be low frequencies for this pipe. If you look on the other extreme, a large pipe is used in penstocks of hydroelectric power plants. In this case, the one of 5.5 meter with a 10.5 millimeter thickness. The limiting frequency of 0.24 Hertz shows that practically all frequencies are those where the pipe behaves in a complex way. Here I shall outline how, by making in situ measurements, we can carry out some specific type of monitoring of the state of the pipe. We start by recalling that the wave propagation along a pipe depends on the bulk modulus and mass density of the interior fluid. Assume that the interior fluid is a liquid. If there is a presence of gas or soft impurities in the liquid, the bulk modulus and thus the sound speed in the liquid may change drastically. The speed of pulsatory wave in the pipe, which is different than the speed of sound because it's affected by the impedance of the pipe wall, can be measured, and we can then use the measurement to fulfill one of these options. If the thickness is known, we shall use the model to identify the sound speed out of measured wave speed. If the sound speed is known, we can use the model to identify thickness out of the measured wave speed. If neither of the two is known, we can use the model to identify both, but for the time being, I am not in a position to reveal how this is done for this third case. Now, how to measure wave speed of pulsating waves? We can measure pressure pulsations at least 3 points along the pipe, then compute a particular cost function out of the spectra of the measured signals, and at the position where this cost function has a maximum, we can then find which is the actual wave speed. Here we shall show how can we monitor either the sound speed in the fluid or the pipe thickness through a concrete example. We take here a steel pipe of 1.25 inch diameter and having the thickness of 3.5 millimeters, and we get from published information about the sound speed in water that at 15 degrees centigrade and 2.5 bar pressure, this sound speed is 1461 meters per second. Now we measure by a technique which I have mentioned before, involving a cost function of auto and cross spectra of signals, the wave speed in the pipe, which turns to be 1393 meters per second. Then we take our model, compute for the pipe which has 1.25 inch diameter, 3.5 millimeter thickness, made of steel filled with water. We can compute the relationship between the sound speed of the fluid and the wave speed. And this relationship is given by this line on this diagram. And then we take the measured wave speed and get the sound speed of 1459 meters per second, which, as you can see, is almost identical to the sound speed taken from the catalog. Alternatively, if we believe that we know the sound speed, which should be 1461 meters per second, we can deduce what is the thickness of the pipe. For doing this, we shall again take the model, but make the computation in a different way, such that we vary the thickness within a reasonable range, and we find inversely what is the thickness which will give the sound speed of the wave speed of 1393 meters per second for this pipe. And we found here that the thickness corresponding to this measurement is 3.4 millimeter. The difference of 0.1 millimeter with respect to the rated thickness value is probably due to either imprecision of measurement or due to corrosion of the pipe which takes place. In our smart analysis, we use several sensors, and we need to have near perfect matching of sensor sensitivities if we are going to get usable results. One of the sensors type which is particularly suitable for measuring the breathing pipe motion is a piezoelectric wire which measures the strain and the hoop strain of the pipe wall. And since we have the model, we can relate this hoop strain to the internal pressure. So in other words, the wire measures the pressure. Now, this sensor is usually hand-mounted by applying a tension during wounding. If the tension force is not uniformly applied to all sensors, a change of sensitivity between sensors may take place, which in turn may lead to unusable results. This effect can be corrected using a particular cost function, which depends not only on the unknown wave speed, but in addition on the unknown ratio of sensitivities of sensors 2 and 3. Again, the maximum of this function will indicate the correct wave speed, no matter the mismatch of the sensor sensitivities. The correction procedure will be demonstrated here. Correct time histories of the measured signals will be used, and in order to simulate the effects of faulty sensitivity, each of 3 signals will be multiplied by a different constant. The first cost function map of the wave speed versus sensitivity ratio is made for the correct sensitivity values. These are indicated by 111 factors. The maximum is at the sensitivity ratio of 1, as it should be, indicating the wave speed of 1351 meters per second. The sensitivity values are then modified as shown on this map. The values now are 092, 087, 116. The ratio of the second and third sensor sensitivities is now 0.75, and these values matches the position of a new maximum, which nevertheless indicates the correct wave speed of 1351 meters per second. Finally, by reversing the sensitivities of the second and the third sensor, the maximum is shifted up to a new value of 1.33, which again matches the actual ratio of sensitivities, yet the wave speed stays intact. So we clearly have an efficient means to overcome an important issue of practical measurements in a smart way. The last example of smart analysis concerns the possibility to reconstruct a targeted quantity, for example a dynamic stress, through backpropagation. The idea is to decompose the measured wave into its forward and backward components and to recompute, using the wave number frequency dependence provided by the model, the targeted quantity in a point away from the measurement area. Here the model will be of major help as it furnishes us with ratios of different dynamical quantities, so we can have access to some quantities which we cannot measure. Where dynamic stresses are concerned, which are related to the components of pipe displacement through different differential expressions, the use of wave decomposition is extremely beneficial because any differential formulation with the wave numbers known is easily converted into an algebraic one and thus easily applied. Here we have an experimental pipe with 3 measurement points marked in red and 2 verification points in blue. The fluid in the pipe, driven by a gear pump, exhibits pressure ripples around the static value of head pressure. The plot here shows the RMS spectra of dynamic pressure directly measured by the sensor 5. These are curves in black. And reconstructed from the sensors 1 to 3, which are away from this measurement point and which are marked in red. The matching is really impressive. Here, the map on the left, where the abscissa is the position along the pipe, while the ordinate is the frequency scale, shows the hoop stress spectrum along the entire pipe. The plot on the right shows the global RMS stress along the pipe, with the positions of measurement points used for the backpropagation marked by red lines. The 2 blue marks show the stresses measured directly. So we again see a very good matching because the measurement and the prediction made by backpropagation agree very well. At the end, I will address a topic which is, as a rule, disregarded by researchers, but which may be equally important as the research itself. This is the question how to transfer the pipe model, which is required in these techniques described before, to industrial users. The model contains complex mathematical procedures, while the end users may have neither enthusiasm nor time to plunge into these procedures. So the solution may be to make a user-friendly pipe databases, but databases which do not contain input data, but which rather contain the results. If we take a particular pipe type, that means a pipe of a given material and filled with a given fluid, all what model needs is the thickness to diameter ratio, which I call zeta here, and the values of normalized frequencies at which the analysis will be made. But of course, when we make the computation, we don't know what zeta and what frequencies the end users will need. So we need to create a database which will cover all possible cases. Therefore, for a particular wall fluid and a particular wave type, we will compute the target quantity, the quantity which the end user would wish to use, for a range of zeta and omega values. Then for each zeta, each thickness to diameter ratio, we shall make a polynomial fit of this target quantity in function of the frequency omega. And we shall store the polynomial coefficients we obtain in this way in the database. This is a difficult part of the work and has to be done by researchers. On the end user side, the deconvolution of the zipped data has to be made. The end user has to specify the ratio of his pipe, the ratio of thickness to diameter, and to get the coefficients from the database, it has to obtain by interpolation the right coefficients, because the database will contain the coefficients only for a series of given zeta ratios. And then the coefficients obtained, the required quantity theta will be obtained by polynomial expansion in omega. So that is the procedure. This procedure will be simple on the end user side. The data stored in a database are drastically condensed, typically by 3 orders of magnitude. The results recovered from the database will therefore contain errors. As an example, let us look at the accuracy of the typical condensation and then recovery procedure. Imagine we wish to zip the pipe coupling function, the one which makes the link between pressure and vibration, for a steel pipe containing oil. We shall use here polynomial fit of order 12, which has been found to be adequate. We have the thickness to diameter ratios zeta as the input variable, and we shall scan it from 001 to 01 to cover practically all possible cases. This range will be divided into 19 steps, and for each of 19 values, the computation of our target quantity gamma will be made for a large number of normalized frequency values, again to cover all practical demands. The exact coefficient gamma for 3 values of zeta is shown on this plot. For 001, 002, and zeta 005. If we now make the computation out of polynomials which has been stored in the database for these 3 values, we shall get an error which will be fairly small. But one reason for being very small is that the values of zeta were those who were used to create the database. More interesting is to see how we can recover the function gamma for the values of zeta which were not used to construct the database. This is shown now here. We have 4 now values of zeta, which are in between the values used for computation. But again, we see that the error is not excessive. The one case, which is the smallest thickness to diameter value, has the maximum error of a little bit more than 2%. So finally, we can see that the idea to have a very condensed database using this play with polynomials can work fairly well. And this brings us to the end of my presentation.